Welcome to this explainer. Today, we're unpacking the high-stakes, invisible engineering hidden right inside the monolithic slabs of modern Indian high-rises. You know, what looks like a simple concrete block from the outside is actually an absolute marvel of precision engineering on the inside. So we're going to explore that hidden world, specifically zeroing in on the hyper-detailed, incredibly crucial process of electrical slab conduiting.
Okay, let's dive right into our project blueprint for today. We'll start with the MIVN construction revolution, then look at the strict 7-day slab cycle, walk through the actual electrical slab conduiting process, review the crucial materials and standards, and finally look at how to avoid common MEP mistakes on site.
Part 1. The MIVN construction revolution.
Now, if you follow construction, you know MIVN technology has completely revolutionized the speed and scale of high-rises in India. It's an aluminum formwork system that lets us cast concrete walls and floor slabs monolithically, meaning in one continuous, simultaneous pour. We gain incredible speed and structural integrity here, but here's the catch. Because there's no traditional brickwork where you can just easily carve out channels later, any mechanical, electrical, and plumbing, or MEP mistakes, are literally set in stone once that concrete is poured.
This really highlights the level of precision required by the workers assembling these pre-engineered aluminum panels. They give us exact dimensional accuracy, yielding consistent concrete shapes floor after floor. But that means electrical fittings must be prefabricated to an absolute exact fit. You have to know precisely where your junction boxes, switchboards, and conduits are going before those panels are locked in.
Moving on to Part 2, the 7-day slab cycle.
To make this monolithic speed possible, we follow a strict 7-day slab cycle. It kicks off with gridline work on day 1, moves to wall panel erection on days 2 and 3, deck panel placement on day 4, electrical conduiting on day 5, an alignment check on day 6, and finally concreting on day 7. But I want to anchor our focus right there on day 5. This is that very narrow, highly critical window where the MEP teams must execute flawlessly. It's literally an industrial ballet where electricians have just hours to lay down the building's infrastructure before the heavy machinery rolls in. Here you can see how placing the deck panels creates the perfect base for the ceiling slab. This essentially sets the stage for the electrical engineers to step in and route the building's nervous system. Just imagine sweeping across this raw deck. This is the exact canvas our site engineers and electricians must conquer on that crucial 5th day.
Part 3, the electrical slab conduiting process.
Now check out the sheer density of the reinforcement steel here. Electricians have to carefully navigate this absolute web of steel, routing their heavy-duty PVC conduits without compromising the structure's integrity. They have to work hand-in-hand with the civil engineers to make sure they don't clash with reinforcement bars, beams, or any embedded inserts.
The workflow is highly procedural, basically executed like a precise military operation. Step 1. Engineers mark the layouts exactly to the approved MEP drawings. Step 2. Electricians bend and route the rigid UPVC conduits. They use bend springs to make really smooth curves so the wires don't snag later. Step 3. They secure those pipes tightly to the reinforcement using nylon cable ties, making sure to maintain proper spacing. And finally, Step 4. Comprehensive QA/QC testing is done before a single drop of concrete is poured.
And a proper QA/QC method statement dictates every single detail of that inspection. The QA/QC engineers act as the final gatekeepers. They're checking junction and fan box levels to ensure everything is perfectly flat. They make sure all joints are completely watertight using PVC solvent cement because, trust me, wet concrete is ruthless. They ensure unused box openings are masked with tape, and, this is absolutely crucial, they inserted GI pulling wear before casting so that cables can actually be pulled through that labyrinth once the concrete cures.
Next up, Part 4, crucial materials and standards.
So, why do we go through all this trouble? Well, while surface wiring is easier to maintain and perfectly fine for industrial factories, a premium residential apartment demands concealed wiring. Buyers expect clean walls with zero visible pipes, which offers superior aesthetics. But concealed wiring means the pipes must be absolutely flawless because they are impossible to inspect once the concrete is poured. You can't just go and open a concrete ceiling to fix a cracked pipe.
To ensure safety in that unforgiving environment, we rely strictly on the Bureau of Indian Standards. If you look at conduit grades, light duty is really the thinnest and only meant for false ceiling runs. Medium duty is standard. These UPVC conduits are the absolute non-negotiable choice for concealed wiring in residential slabs and walls.
Heavy duty, the thickest, is reserved for industrial, surface, or underground work. Choosing the correct grade prevents the pipe from just crushing under the weight of wet concrete and heavy site boots.
And here is the amazing part. If you do it right, if you use ISI-marked, properly sized conduits and install them strictly to code, this invisible infrastructure will safely last 25 to 40 years without any intervention. It's a massive lifespan, but it's entirely dependent on the decisions made during those few crucial hours on day 5.
Which brings us to Part 5, Avoiding Common MAP Mistakes.
Let's troubleshoot the most catastrophic failures made on the slab. These critical construction failures read like a nightmare for any site engineer. A huge one is using unbranded non-ISI conduit that gets brittle and cracks. Then there's the mistake of overfilling pipes past the maximum fill ratio, which leads to overheating. Pulling single wires through metal conduits is another big no-no. But two of the absolute worst mistakes involve structural coordination, missing expansion couplers, and clashing with mechanical slab penetrations.
Let's talk about the expansion joint danger, because this is a frequently overlooked disaster. High-rise buildings naturally move and settle. So when rigid electrical conduits cross structural expansion joints, they absolutely must have expansion couplers installed. If this step is skipped, as the massive building settles over time, those rigid pipes will simply snap in half inside the concrete, totally severing the building's power.
Then there's the human element, mechanical clashes. The mechanical team obviously needs to cut holes for their plumbing and HVAC shafts. To prevent them from accidentally cutting straight through your freshly laid electrical lines, proactive site engineers always mark and provide plywood blockouts or sleeves for mechanical penetrations before a single electrical conduit is laid. It is basic coordination, but it saves millions in rework.
At the end of the day, proper coordination across all these trades and strict adherence to regulations are what keep the electrical network safe. The entire system has to survive the moisture of the wet concrete, the intense vibration of the compaction needles, and the immense load of the slab itself. Precision engineering is just absolutely critical.
So, I want to leave you with this final thought. As the slow-motion concrete pour covers the completed slab, catching the golden sunset, ask yourself, what happens when a cheap, non-certified conduit cracks and collapses inside a solid monolithic concrete slab? It traps wires inside a monolithic slab forever. It's a massive mistake you just can't undo, proving exactly why precision engineering in the MIVN process is absolutely vital. Thank you so much for joining me on this deep dive into the hidden engineering of our modern skylines.